Okay, I want to show you guys something pretty cool today. All right, so.
No, but like they go and tell them.
Okay, put your stuff away, please. Let's take a quick look here. I want to just do one problem from 8.1, so make sure we got that down. Remember, this is the stuff. I think there were a couple people gone. This is the stuff that had to do with Kepler's laws, right? And it's the quick history. If you were gone that day, Copernicus first noticed that if you look at the orbits of planets, they do weird stuff. They exhibit this retrograde motion tendency where they'll be going forward across the sky and then they'll jog backwards a little bit and then go forward again. If you look at it over a period of days, which is strange. So the way that we can explain that would be if, unlike what people thought at the time, if the planets weren't orbiting the Earth, if they were orbiting the sun along with us, that would explain that retrograde motion. So that gave us the idea, gave Copernicus the idea that that's what was going on. Kepler was a math type guy, and so he took that a step further, and he came up with some laws that describe orbital motion, right? And so we looked at this the other day. There's a bunch of stuff up online you can kind of play with. The first two are just kind of qualitative, explain how this would look. We know that the paths of planets around the sun, or it could be satellites around the Earth, or anything orbiting something else, the elliptical path, or the orbital path is going to be elliptical if it's in a closed orbit. Okay, now, if we went a little further with that, if the planets, what would happen, and this isn't in the book, but this is just interesting to know, what would happen if an object, let's say, entered the Earth's gravitational field, which is a little hokey because it goes forever, but it enters a place where the Earth's gravitational field was substantial, and it wasn't going that fast. It's going to get captured into what kind of orbit?
The sun.
Well, what's all orbits are what? Elliptical. Okay. But what do you think would happen if the object were coming through really fast, so fast that it wouldn't get captured? It would warp. It would get warped a little bit, right? And so it's going to look something like this. So if this is the Earth, and let's say here's an elliptical orbit of some satellite that's trapped. That's pretty bad ellipse. I can do it again. Something like that. There's an elliptical orbit, right? Some object that got captured. But now we've got some object that's coming just blazing through. It's going to come through and it's going to get bent very slightly until it gets close, and then it's going to get bent and appear to go off almost straight. Did you guys in pre-calc, I would think maybe you talked about what that kind of shape is? Does that look familiar?
Obtuse angle.
Is that an arc? It's not an arc. No, it starts with an H.
Hypotenuse.
No, it sounds like hypotenuse.
Hypotenuse.
You have never seen it? Hyperbola? You talked about hyperbola and pre-calc?
Oh.
Okay, that's what you get. So a hyperbola is the type of orbital path you get if the object is going fast enough. If it's going faster than what we call escape velocity. You've probably heard about escape velocity. We'll talk about it a little bit today.
So is this one with escape velocity?
So escape velocity is how fast something would have to go to never come back. Right. And there's a number we can give to that. I don't know if we'll get to it today, but either today or tomorrow.
Escape or escape?
Escape.
Escape.
Escape velocity. So you're going to escape the Earth's gravitational pull if you're moving at a certain speed. I think it's, I can't remember if it's 11.2 or 13.2 kilometers per second. It's fast. So it's got to be going fast. So like a bullet doesn't even go in close to fast enough to do that, right? But theoretically, if you shot a bullet fast enough, if the gun were fast enough and it was coated with slip ring or something, so it wasn't going to get disintegrated in the friction with the air, theoretically, it would, if you did that, it would never come back, right? It would just escape along one of these hyperbolic trajectories and be gone.
Why wouldn't an object traveling any number faster than 9.8?
Well, I can prove it to you right now. I can throw a baseball up.
Well, yeah, I know, but that's because it doesn't have any acceleration on its own. Like if we gave it
Oh, but
a
we're not
rocket-
talking about anything that has acceleration on its own.
Oh.
We're talking about a
Initial
just an
velocity.
object that's traveling through without being sure. I mean, if I have a rocket that's got powerful enough boosters, it could accelerate up at 0.1 meters per second the whole time and just never stopped, right? Agreed. But that's different. That's cheating. It's got a source of, of thrust that's pushing it upward. Yeah.
So this is kind of related, but you mentioned a bullet. I have a question for you.
Mhm.
When you shoot a bullet and there's bullet rise, is that because it's in an orbit and it's moving faster? So it's
because
orbits.
No, it's because I think it's probably just
Your
because.
scope's mounted above your barrel, so it has to go up.
Right.
Like
No,
it's,
no, like when the bullet rises.
But it's rising because you're targeted in for some range. Like let's say you're targeted in for 300 yards. For this thing to not drop to get to 300 yards, it's got to go up initially to get there because it's going to arc a little.
Yeah, but what causes it to rise?
Because the barrel is pointed up a little bit. Because all you're doing
I
is.
see what you're saying.
so it's
See what I'm saying?
It's like
Yeah.
you're looking at this angle, but the barrel's at that angle, so that it'll
Yeah.
hit when you get to
So
that
that
spot.
would
Right, because it's going fast, but it does drop, right? I mean, it's in the air for a very short period of time when it's going a long ways away, but it does fall a little bit. Okay, so then, what do you think the in-between shape would be? Because if an object came in with just the right speed, it would be exactly at the one perfect speed to be between an ellipse and a hyperbola. And so what that would look like, essentially, is an ellipse that would just never turn. We could say in a sense that it's an ellipse that would turn at infinity. Okay, can't ever get to infinity though. What do you think the in-between shape
It would
is?
never come-
So it is, it's a parabola. It is. It's a parabola. So the in-between shape is just gonna be something that's gonna look like that, which is a parabola. And a parabola really does act like an infinite ellipse. That gives you a little insight into what a parabola really is. It's like an ellipse where one focus could be, we know where one focus is. A parabola has a focus. Where's the other focus? It's like an ellipse where the other focus is infinitely far away. Okay, and that's, if something were traveling on an elliptical trajectory, it would have just the right amount of orbital speed so that it would constantly be losing speed, and as its distance from the Earth approached infinity, what would its speed approach? Zero. That's not true on a hyperbolic trajectory. It's got carrying an excess of speed, and so it's never going to approach zero. It's going to always be moving at some finite speed. It's never going to drop below some finite speed, right? Just gives you a little idea about and we'll talk about this soon in terms of orbital energies. Now, that's coming down the pike. But okay, so anyway, moving forward. So we said that paths of planets, because they're captured, are elliptical. We would say, and we will say, that an ellipse, a closed orbit like that, is going to have negative orbital energy. It doesn't have enough to get away. Hyperbola would have positive orbital energy because it's going to have enough to get away and then some. A parabola would be in between. What do you suppose its orbital energy is? Zero. Yeah.
So would a hyperbola, like when it went through that warp or whatever,
Mhm.
would it increase in speed to where when it
It's
was on the other side, would its velocity be higher?
so it would be the good question.
Cancel itself out?
Without any movement of the planet, it would have the same speed. Like let's say that I drew this really poorly, but let's say that's supposed to be, what do they call that? That's the line of symmetry of the hyperbola. So if we made a circle right there, at that point and that point, which are equidistant from there, the speeds would be the same. So it's going to be picking up speed through here, and then it's going to be gradually losing speed up there. But if the planet's moving, that's where you can get that slingshot effect we talked about the other day, right? If it's moving, you can actually capture some of that speed as the planet's moving this way. You can capture some of that speed when it shoots off, and you can steal some momentum from the planet and capture it in the spaceship. And that really works. I mean, like if you want to get, this is kind of a,
So we can Martianing all around.
you could, and it's kind of counterintuitive, but like when we want to launch, what were the ones that we launched? Voyager and those ones that went way out, and they're actually outside of the solar system now. Well, to get them going fast enough, we launched them in the opposite directions, but we launched them in such a way that they would capture some orbital energy from all the big Jovian planets, Jupiter and Saturn, so they'd get kind of bombarded around and gradually pick up all this orbital energy, and then when they finally leave, they're really cruising along.
Oh, that's smart.
That is smart. Those guys at JPL and NASA are pretty smart.
Is there an escape velocity for our solar system?
There is. Yeah, and we could calculate it. We assume we can calculate it. Yeah.
Would the velocity change depending on like where you picked your path to
It doesn't change much from Earth because Earth seems pretty bumpy to us, but this is true story. We have big mountains, Mount Everest looks pretty big, Mount Hood looks pretty big. But if you take the surface of Earth and you compare, it is a little bit, it's an oblate spheroid. It's a little bit warped out in the middle, it's got a little bit of a bulge because it's rotating, and so it kind of splays out a little bit. But other than that, if you ignore that slight, equatorial bulge there, the surface, if you compared it to a billiard ball, say a cue ball, which do you think has, relative to the size of the ball, has bigger mountains?
With what you're saying.
Yeah, basically, you can guess. I mean, it doesn't seem like it should be, but the cue ball has much bigger mountains than Earth does. Much bigger.
How?
It's because you're used to seeing these mountains from being just a little flea on this big planet, right? But if you were to, move far, far away, you can't see those mountains anymore, right? They're just, they're too small. You can see some shadows and things, right, depending on where the sun is. But that has to do with the fact that the wavelength of light is a lot smaller than the size of those mountains. On a billiard ball, that's not the case, so you can't see the shadows as well. But anyway, the surface of a billiard ball is rougher. The aspect ratios between the peaks and the valleys are larger than they are on Earth. So the Earth is pretty, right? So Earth is pretty smooth, and so in answer to that question, it doesn't really matter where you are because you're always pretty much the same distance from the center of the Earth. The gravity changes very little on the surface of the Earth.
So-
It does, measurably, but it's microgravity. It's really slight variation.
So if the cue ball was the same size as Earth,
You would have bigger mountains.
that's so weird.
Yeah.
Well, what about like the
They feel
solar
so
system?
smooth. It's crazy.
Since you might encounter different planets going different directions.
Yeah, you're right. So you'd have to assume that you're just going to take an average and assume you're taking an average path. But that could easily get messed up if you happen to run into a planet or something.
Yeah.
That's
Planet.
Okay, so then we said paths are elliptical. We said this was kind of cool, right? This was the thing we looked at where if you look at the orbital area swept out when an object orbits something else. I just got to pull this one up. Was anybody not here when I showed this? Seems like there's some people gone. Oh, she's not here now, so I won't worry with it then. You've already seen it. But this was that kind of cool deal where the area swept out by the orbit is the rate at which it's sweeping out area is constant. So over any fixed period of time, the area that it's sweeping out is always going to be the same. That means when you're really far away, of course, you're not having to move very fast because those are big, long sectors that you're sweeping out, right? So they have a lot of length to them, so they don't need very much width. But when you're close to the object, when you're zinging by it, then they're not very long sectors, and you have to carve out a lot of angle to make up that extra area, right? And we saw that in action. The only one that's really quantitative, though, that we can really use is the third one, which tells us the idea that the square of the ratio of the periods is equal to the cube of the ratio of the orbital distances, right, from the centers of mass of any satellites. That's useful. And we looked at a couple examples, one or two, I can't remember. Maybe we just got through one. We did this one, and I think that was it. So let's try maybe another one of these. So how can we do something like this? So can we calculate we know that on average Mars is 1.52 times as far from the sun as Earth. Okay. Predict the time required for Mars to circle the sun in Earth days. Okay, so how are we going to do that?
So Mars radius b.
Okay, so which one now? And this is really helpful. We've got object A and object B. Which one do we want to be object A? The one that we know or the one we're looking for? One we're looking for. So A represents Mars, B represents Earth, right?
So 1.52 is going to be R sub A.
Okay, good. So then what does this become? So the period, we could say that the period of Earth, that's
B.
going to be B, right? So the period of Earth is going to equal how many days?
365.
365 and a quarter,
365.
roughly.
Yeah.
365.25. You might be asking, where the heck's that 0.25 come from? That's why we have leap years, right? Every 4 years, you got to have a year that has one fewer days. If you're born on that one day, that's really unfortunate. Although maybe it's good, because then that would make me a lot younger if I was born on a leap year. That'd be a good thing. And then actually, it's not exactly, here's another thing too. It's not exactly 0.25. It's 0.25 something. And so leap years, every once in a while, like every 4 years, you have just a standard leap year. But then there's some other weird thing that goes in there too. I don't know what the amount is, but like once every 100 years or something along those lines, you have to do something else weird, like add an extra day or subtract an extra day. So there are these really oddly spaced leap years that are even different than a normal leap year. So, but I mean, you've never experienced one, I never have. They don't come very often. If I haven't experienced it, they must not come very often.
Wasn't there a leap second, like last year or this year or something?
I don't know about a leap second. See, that's where you do the year thing. So then it would be, if there were a leap second, then after however many seconds there are in a day, 24 times 3,600, after that many years, you would have to add or subtract an extra day, right? Yeah. All right, so then that's the period of the Earth, right? We're looking for the period of Mars. What is the radius of the Earth? One, exactly. We'll just call it 1, right? We'll call it 1 R sub E, because all we're really saying up here is that Mars is 1.5 times as far away, right? So what we could do instead is say the radius of Mars equals what?
1.52.
1.52 times the radius of Earth, right? And look what that does to our equation there. So we end up getting T sub m over 365.25 squared equals R sub m, which is 1.52 R sub e over R sub e cubed. But what's the advantage of that?
You gotta cross out R sub E.
Yeah, I can just cancel out the R sub e's algebraically. So really all I need is that number 1.52, right? So how would I solve this then?
Cube the 1.52.
I'm going to cube that.
And then
I'm going to square these, right? Do you agree? Okay, so I'm going to get T sub m divided by 365.25 squared equals 1.52 cubed, right? All I do is just multiply each side by that. Does that make sense?
No, you wouldn't have this.
Oh, sorry, that's going to be T squared, right?
Yeah.
So then I'm going to multiply each side by that, and then I got a square root, right?
Well, couldn't you just cube the 1.52 and then take the square root of that number?
Okay, that's a good point. So we could make this a little quicker, couldn't we? We could say instead of having to go through that whole process of squaring this and square rooting it, why wouldn't we just square root it from the start, right? We could just take a square root of both sides. Whoops. Square root of both sides. And what's that going to give us? Over here, it's going to cancel the squared. Now, what's that going to do over here? You could write this. It's a little bit weird to say the 1.52 cubed square root.
Isn't it like
you can.
1.52 to like the 2/3?
Okay, it's something like that. Here's the thing I want to show you. It's a little trick, and this helps when you're calculating things on a calculator. It makes. Have you ever been in that situation where you're trying to take, let's say on a calculator, you got to take a cube root or a fourth root of something, and you're hunting around for the cube root button, but it's not there. You got to go through all the menus to find it, right?
It's just math.
If you haven't been there, you'll inevitably be there at some point.
Yeah.
That's it, right. So the trick is, a radical is just going to be a fractional exponent. So if this is a square root is really just a second root, right? And so to take a square root, you could just take something to the,
3/6.
yeah, the power of 1/2. So if I want to take the square root of 17, that's the same thing as saying 17 to the 1/2. If I want to take a fifth root of 83, that's the same thing as 83 to the what power? The 1/5, right? And so how can we use that up here then? Well, I've got, think what this is equal to. This is equal to 1.52 cubed. If I square root it, I'm just taking it to the 1/2 power. Now think back to your properties of exponents. It may have been a while. But if I take a power to a power, what do I do to the exponents? You multiply it, right? So this is the same thing as saying 1.52 to the 3 times 1/2, which is 3/2. Okay? And so when you think about that in the future, you always know that the numerator is going to be the integer exponent, and the denominator is going to be whatever the index of the radical is. That's always going on the bottom, right? So we could just say jump right from there probably down to there, okay? And you can just enter that on a calculator, okay? So then what we finally get, if this is equal to that, I just have to multiply both sides by 365.25, right? So the period of Mars equals the period of Earth times the radius of Earth. Oh, sorry, I'm sorry, we already got rid of those, didn't we? The 1.52, which is the ratio of the radii. So times your 1.52 to the 3/2. It's not linear, right? It's not like if the radius is increased by a factor of 1.52, it's going to directly make the period that much bigger. It's going to be different by that amount instead. So what's that going to be? Do you think it's going to be, do you think that, just make a guess here, do you think that the period of Mars is going to be greater than 1.52 times the Earth year or less?
More.
It's going to be more, isn't it? Right? How do you know it's going to be more?
Because the radius is 5.
Okay, because yeah, if the power is greater than 1, it's going to make it bigger, isn't it? Right? And that's 1.5. So on your calculator, all you've got to do is this. All we've got to do is just take our 365.25 times 1.52. Do I even have to make that a fraction? I can just say 1.5. 3/2 is the same as 1.5, and that works to the 1.5 power, and that's your answer. Okay? So it almost doubles it, right? That's why you get such really big orbital times for planets that are very far away, like Pluto, which I know isn't really a planet, it's a dwarf planet. I mean, it's well, what is it? Let's look it up. I know it's really a long period.
There was no. By the way, we had a leap second this year or last year on December 31st.
Oh, okay, 248 years for Pluto to circumnavigate the sun one time. Yeah, because it's very far away. And look at how that works. You know, r to the 3/2 is going to make things bigger.
Yeah, it only takes
faster.
one. It only takes one.
All right.
Is 1 year relative to us?
Yeah, 1 year. 1 year is Earth. Yeah, that's 1 year is defined as the amount of time it takes Earth to travel around the sun one time. Yeah, I mean you could say it's an Earth year, but we always measure everything in Earth years because we live on Earth. Makes sense.
Imagine how long that. Like if you were born in winter, your whole life would be in winter.
Yeah.
Oh.
Yeah.
Okay. So I thought of this yesterday, but so say you're an intelligent life on a distant planet.
Mm-hmm.
Okay. Yeah. Would you have a sleep cycle and an anatomy that just goes with a lot less or more sleep, depending on like relative to humans and most animals here?
I don't pretend to know the answer to that, but in my opinion, it would be almost certainly you would. You would be adapted to. Well, I can prove it. I can prove it. Okay.
He's gonna stay up 24 hours.
No. You want? I can. I got all kinds of good stories for you. That brings up another good story. So here's a story. So it turns out that the Earth was formed. Let me know the time. I want to say it was about 1 billion years after. I got to know the time is sort of relevant, so I want to know the time.
I found that funny.
So let's see. Oops. Didn't Google great.
Let's Google it.
Okay, so best understanding of the prevailing, I would call it a theory, but it's a theory in the sense that we know what happened, but just all the ins and outs are not totally understood. Would have been about 30 to 50 million years after the origin of the solar system. So that would have been roughly about the time that the Earth was formed. So very shortly after the Earth was formed. So it's been formed for a long time, but for a long time, the Earth was formed by a planetoid about the size, or the moon, sorry, about the size of Mars, crashed into the Earth during the period of heavy bombardment in our solar system. It ejected a huge plume of molten rock that just would have been in a ring around the Earth, but in a relatively short period would have come together to form this glowing ember of molten rock that would have been the moon. Earth would have been liquefied also. The whole surface of the Earth would have been liquefied, so that would have been a bad time to be around. After a while, things cooled down, and the moon cooled down, but it was much closer to Earth, much closer. The moon would have been in the night sky. If you were even to go back, like even just like a billion years ago, the moon would have been enormous in the sky. Would have taken up. Well, I don't remember the exact numbers, but it would have been, like 10 times as large across as it appears now. So it would have been really large.
So it's like playing in the field.
And so at that time, the Earth was spinning much faster than it is now. Days at that time were only 12 hours long. Okay, how do we know that? This is interesting. There's a way you can know that. There's a type of algae that lived in shallow seas at the time, that the shallow warm seas, and there was so much incident radiation.
Yeah, wouldn't the seas be huge, like all
See,
the waves?
yeah, they were big, but there were a lot of really shallow areas. And in these shallow areas in the warm water, these things grew so fast that there was a daily growth ring that was laid down. Just, you could actually see how much they grew by day. They grew in the shape of these big, like mushroom things that were just under the water. And they were called, no, they weren't. They were called fulgurites or something like that. I can't remember. But we could look it up. I'll show you pictures of them. We find fossils of these things. And when you look at the fossils, if you cut through the fossils, you can actually see the daily growth rings. But tell me what's going on. When you look at the daily growth rings, here's what you see. This is really interesting.
Do they have any pictures of the fossil?
Yeah, I'll find them. I'll find what they look like. I'll pull up a picture. But here's what the rings would look like. So if you're looking at, let's say this is going to be amount of growth. So this is going to be like the thickness of the rings. And this is going to be time in days. What you'd see is they would do something like this. They would have these big periods of growth, and then they would get a little bit smaller, and then they'd get a little bit bigger. So what's responsible for the really small ring pattern? Days. What's responsible for this longer pattern? Seasons. So how many days were there in a season? All you have to do is count the number of rings, the small rings, oscillations in one of the big rings, right? And it turns out there were about 450 instead of 365. So the Earth was turning quite a bit faster. And you can go back, the earliest ones are even more than that. I want to say it was 18-hour days, not 12-hour days. That's what it was, 18-hour days. So the Earth was spinning much faster. But if you look at some of the fossils from the time, it can be inferred that these little creatures behave much as they do now, and so they were adapted to a longer day. There's, you can look at where they lived and the same kinds of patterns for them. For these calcareous creatures that laid down lots of calcium really rapidly, and so you can see that, yeah, there's your answer. So the best I could do is say, I don't know for sure, but based on like that, it sure seems like they would have circadian rhythms that would be adapted to the day, right? Which would make sense. Okay, well, that was a big sidetrack. Back to business. Oh, you want to see a picture of those? Okay.
Wait, aren't there videos of air cannons on YouTube?
Oh, no, fulgurites are different. Okay, I knew fulgurite was something. These are kind of cool, too, though. I'll show you a picture. You make sure. I got to preview this. Hang on here. You never know what you're going to see. So, does anybody know what causes that? Those are rocks.
Oh, lightning strikes.
Yep, lightning strikes. Yeah, fuses the sand. Yeah.
That's not a fulgurite.
So those are fulgurites. Yeah, but what I'm talking about is not a fulgurite. They're called. It had.
I literally said this is not a fulgurite.
Which one did? Oh, that one right there. Oh, that one was not a fulgurite. I got you. That's not a fulgurite, but those are, and that is.
No,
Yeah.
that's what's not.
This is not.
Oh, that one is then. Okay, yeah. The ones I've seen, you can create them. I've seen them done. They did an experiment when I was in college where they attached a lightning rod. They did this in Arizona, but it was a Stanford research group that did this. They attached a lightning rod to this big vat of sand, and they would go down into they'd drive this thing down into these thunderstorms until they would get a lightning strike, and then they would create these fulgurites and study them. Yeah, it was pretty cool.
Wait, so what is that if it's not a fulgurite?
I don't know. Some kind of tree or something. Who knows?
I knew that was a lightning strike because I saw it on Twitter.
We thought they were called.
You saw it on Twitter.
I saw it on Twitter.
Nice. Twitter can be educational, I guess. So they're called hematite. That's what I think, maybe. No, that's not it. I can't think what they are.
Just look up ancient acronite.
My favorite one's like, haha, got you. I'm like, geez, really thought you made that.
Oh yeah, exactly. Finding the right transparency so you can't see.
Stromatolite. That's it.
Yeah.
Stromatolite.
Oh, I could have told you that.
I know. I should have asked you. Okay, so here's what they look like. If you go down and look at there's when you see them fossilized. So there's when you cut through the fossils, that's what you see. There's those growth rings. And this is what modern stromatolites look like. They're still growing in some places. That's what they look like. They just accumulate algae on the outside at a really, at that rate where it's...
So are those rocks?
They look like rocks, but they're not. But when they get fossilized, yeah, then they're rocks.
Wait, so is each one of those rock-looking things sticking out of the water is actually a plant?
Yeah. Actually has a coating of algae. It's like coral. It has a coating of algae on the outside. And then it gets, it gets fossilized,
So
and
they
there's...
grow over each other.
Yeah, exactly.
They fossilize it. It fossilizes itself.
Well, yeah, because there's calcium left behind, and
That's
so
so
it
weird.
kills the plant inside, but then it grows on the outside.
Use those to build things?
I don't think so.
Can we use those?
That'd be cheap.
Yeah, I think that is cheating.
Use it as a way.
And
So-
let's launch them into the cavern.
Anyway, I thought there might be some...
It'll grow and break more stuff.
Well, it wouldn't take me days to grow those for days.
I'm pretty sure the plant practice is like decay.
Exactly, then we win.
Checkmate.
You don't have to point out
So
so
close.
close like that, okay? Those are just
It's one of those.
Okay, this is kind of one last thing I'll show you. So that's sort of what they look like, right there. Right, so there's this little growing tuft. They wouldn't be that green, but the little growing tuft, and they form those rings. Right, there's a cross section. Anyway, I learned that in a geology class.
What's
I
your
thought that was pretty
definition of a cross section?
Cut through
What
it.
is a cross section?
When you cut through it,
Cuts.
yeah. Mhm.
You say it all the time about like.
And that's it. A section means a cut, and it's literally crossing through the middle. Yeah. Okay, so you guys are going to get some. I'll skip the rest of that. So you guys will get some more practice with those. You can mess around with that Kepler's third law. Okay, here's the thing I want to show you today, though. I don't know how much time we got. 8 minutes. We can kind of get started on this. Okay, so the law of universal gravitation. So this is and there's a really cool story behind this. The law of universal gravitation. All it is the equation that predicts the strength of gravitational attraction. So the gravitational force acting between two things, and this is it. The law of universal gravitation tells us that the gravitational force acting between objects A and B is equal to this universal gravitation constant, which is really small. It's like 6.67 times 10 to the negative 2. No, really big number, negative 23 or something. Really, really, really large number. I mean, really, really tiny number. Right, so it's very, very weak, which tells us how weak gravity is. If you compare gravity to the other forces, it's very, very weak. Yeah, really big. This is really, really small. This is the other one. Really small. Anyway, it's this very small constant, capital G is the letter we assign to it, times the product of the masses, and that makes sense, right? Wouldn't you have probably a bigger gravitational attraction if the masses are larger?
Yeah.
Right. That makes sense. Earth attracts us a lot more than that does, right?
Oh my
You don't feel
gosh.
yourself getting drawn to that too strongly. right? So that's not very massive, and so there's not much gravitational attraction.
But does that weight have gravity, like gravitation?
It does. Okay,
So
so
like,
if I
you got
did,
something small enough, it would like orbit it?
right, so let's pretend that we had the budget to go into deep interstellar space. We don't, but if we did that, if we left these two masses sitting perfectly still in deep interstellar space, free of any net gravitational field, what would happen?
Wouldn't you have gravitational?
Yeah, okay, but I'm gonna leave them there, and then I'm gonna just jet out of there. So we're gonna watch it remotely.
Yeah, would they start like?
So what's gonna happen? We're gonna do that. But how quickly would it happen? Well, we can calculate it. Well, maybe we'll do a calculation like that.
Well, the smaller one would move.
It would be very, very slow though. This process might take a long, long time to happen because they're very weak.
Like 30?
Oh, I'm gonna say it'd be probably on the order of maybe even hours before they.
Oh, I was thinking years.
No, I was thinking
years. I thought when you meant.
Well, we could,
I was
I mean,
kinda joking.
we'll remind, next time we meet, we'll just throw in some numbers and do a estimation. All right. Okay, back to business. So, anyway, the product of the masses makes sense, but here's the part that was interesting. It's proportional, or it's proportional to the inverse of the square of the distances. And so this is, like many things in physics, we call this an inverse square law. So this tells us then that if I double the distance away from something, let's say I'm instead of being a meter away, I'm gonna move these things 2 meters away. What's that gonna do to the gravitational strength?
Less than that.
By a factor of
2.
no,
10.
G
Square.
squared. So if I double the distance, then that's gonna cause the force to go down by a factor of 4, of 2 squared, right? So gravity, not only is it very weak, it gets weak fast too, right? Gravity is by so far the weakest force in the universe, and yet it's the dominant force in many ways because it's the only one that is always attractive. It doesn't, they're like electromagnetic forces, as we'll see. Electric charges can both attract and repel depending on the charge. Gravity doesn't do that. Gravity only attracts. And so even though it's incredibly weak, if you get enough stuff globbed together, to use real technical terms, you can create massive gravitational forces that just rewrite the whole shape of the cosmos, right? So we see that, black holes and galaxies and things, yeah.
Did you separate the gravity and the mass A and B to just make it simpler to see or to visualize?
He didn't come up with this law.
I'm not that old. I didn't develop this law.
Why is G
Does it
separate?
order of operations?
Okay, why is G separate?
Yeah.
Because G is the constant, right? Really, all this is just G times M sub A times M sub B, all divided by D squared. But we put the G outside of that because the G is the number that never changes. That's got a value that's in a book somewhere. You'll see it in your textbook. That doesn't change. All these other things can change, right? We can change the masses of things. We have different objects with different masses. The distances can be different also. But here's the part that I'm not going to get to today, but I want to really impress on you that this is so amazing to me that people did this. We could do this right now. We could literally mass the Earth. When I say mass the Earth, mass is a verb in that case. We could determine the mass of the Earth and never leave the physics lab. We could.
Google.
Wouldn't even have to do that. Wouldn't even have to do that. I mean, we could. You're right. But how did people come up with determining what the mass of the Earth was? Because once you know this law, you can kind of figure it out. But before this law was formed, the guy that did this was Henri Cavendish, and he built this there aren't many of these kinds of experimentalists around. He built this amazing piece of equipment that was just, he built it with metal and wire and things, and it was sensitive enough that he was able to essentially find the mass of the Earth. And the way he did that was he determined what the universal gravitation constant was. That's all it took. Because we've known for a long time what the radius of the Earth is, roughly. Right? We can do that. We can do that right now. If we just took 2 people with pretty good watches, and we had a little bigger budget for our physics department than we do now, we could send one person to the equator, someplace on the equator. And how do we know they're on the equator? Well, they would know that there was a time during the day when, if we went to between the seasons, there's a time during the day when a stick casts no shadow, right? Okay. We'd send somebody else north somewhere, right? And a distance that we know though.
North Dakota.
We could estimate that somebody's gonna go north by, let's say, 500 miles. Send them north 500 miles. And that's been easy to estimate for a long time. And then at a specific time on a specific day, you may have to know the time, you could just chart what's the longest shadow that a stick would cast, or the shortest shadow, I'm sorry, that it would cast on a given day. And that's gonna tell you, as long as the stick is a known height and you're putting it in the ground so it's perpendicular to the ground, that would tell you essentially how big the Earth is, because think what you're getting there. We're not gonna go through all the math, but what you're finding is pretty cool. When you do that, so let's say this is the Earth, right? If this is the stick that's on the equator, right here, and this is the stick that's up here, right? The sun is going to cast a certain shadow up there, and it's not going to cast a shadow there, right? If you know, would you agree, we're not going to do all the math, but would you agree that if we knew this distance, and we knew what those angles were, we could pretty easily figure out the thickness of the Earth, right, the radius of the Earth?
Yeah.
Right?
I know an easier way to get it.
We'll pick it up later. Yep.
Oh.
You guys get mostly work week, yeah. Yeah, I think, actually, you guys do, because we finished up yesterday.
Yeah.
Yeah.
So we have